Welcome to Lecture 2 of Microeconomic Analysis 1 with me, Dr. Craig Webb. In today's lecture, we're going to be looking at demand, at supply, and the idea of an equilibrium. These are quite simple ideas today, but they are very powerful and fundamental for economics. There's lots to do, so let's get started. In today's lecture, we will be looking at demand, supply, market equilibrium, and once we've covered these concepts, we'll have a look at some comparative statics, what happens when we shock the equilibrium, when something changes, how do equilibrium prices and quantities supplied and demanded change. So let's get started. When we talk about quantity demanded in microeconomics, we mean the amount of a good that consumers are willing to buy at a given price, holding constant other factors affecting purchases. An important thing to notice about this concept is that quantity demanded does not mean the amount of a good that gets sold. It means how much the consumers are willing to buy at a given price. So if only 10 units of a good are available, that is the most that could be sold. But in principle, the consumer could have been willing to buy a lot more than this. And when we talk about demand, that's the amount we will be considering. Now, how demand is formed, how consumers decide how much of a good they're willing to buy, depends on many things. So the main thing we will focus on throughout this semester really is the goods market price. That's going to be the key thing of interest for us. Also, we'll be looking a lot in lectures 4 and onwards at the idea of preferences. So how do we model and describe a consumer's tastes? These are unique and individual to each consumer. So we have to have a way of modeling this and to show the connection between their preferences or tastes and the consumer's demand for a good. Other things to consider are the prices of other goods. These goods might be substitutes, so goods that you could buy instead of a particular good, or complements, goods that you typically buy with the good that we're interested in. Of course, their demand's going to depend on how much money they have to spend, their income, and other factors such as government regulations, peer effects, the season. So you could imagine that in winter, certain goods are far more in demand than they would be in the summer, and vice versa. So many other things, advertising and so on. We're going to keep things simple and typically focus on a good's own price and include, what's frequently included in microeconomics is a good's own price and the prices of other goods that are available and the consumer's income. They will be the main variables we will focus on. To capture the idea mathematically that a consumer's demand depends on several variables, the way we model this is using what's called a demand function. So a function is a mathematical device where we input several variables and out pops a number in this case, which is the quantity demanded. Typically, in microeconomics, we're going to assume that a demand function is a function of a good's price, of the prices of other goods as well, and of the consumer's income. So we might write Q, the quantity demanded, is equal to some function capital D, which depends on the price of good 1 all the way to the price of good N, and the consumer's income. Now, of course, in real life, there will be many other variables that are relevant, but this is the typical starting point as we model a demand function. To give a simple example, consider a model we will look at today for the demand for coffee. So we might imagine that the demand for coffee, Q equals D, which a function D, which depends on P, the price of coffee. It depends on PS, which is the price of sugar, which is a complement, something you might typically purchase when you purchase coffee, and also capital Y, which is the consumer's income. So that would be a very simple demand function. We've left it quite general here. It could take any functional form at the moment, but we're assuming that it only depends on three things. At this point, let me mention a very old idea called the law of demand. So the law of demand essentially states that demand for a good and its price, holding all other factors constant, are negatively related. So, holding everything else constant, if a good gets more expensive, people buy less of it. If it gets cheaper, then people buy more of it. To express this conveniently in mathematical notation, we simply write that the partial derivative of demand with respect to the good's own price is negative. Okay, so I'll talk a little bit more about partial derivatives in a moment, but really the idea just means I'm differentiating the demand function. Now here demand depends on possibly many variables, so it's a many-dimensional function. I'm going to assume everything else is constant apart from a good's own price, and then take a derivative. That's what we mean by a partial derivative. Another way of expressing the idea of the law of demand is that when we draw a typical diagram with demand on the horizontal axis, unfortunately, and price on the vertical axis, then demand curves slope downwards. Okay, so we'll draw some diagrams today and notice that we typically draw them the wrong way round, with price on the vertical axis rather than the horizontal axis, which is how we really think about demand functions. So this law of demand is it's an empirical phenomenon, really. When I say empirical, I mean it's something that we observe in the data. It's by no means a law implied by rational behavior. So if we were to observe a violation of the law of demand, we couldn't say that the neoclassical theory of microeconomics has been contradicted. Not at all. It's perfectly rational to violate this law. It's just that we very, very rarely see violations of this law. Okay, so almost all of the time, what we see is the law of demand being satisfied. Goods that do violate the law of demand are called Giffen goods, and we will study Giffen goods a lot more in later lectures. The idea was originally proposed by Giffen, who observed or suggested that during the Irish potato famine, because potatoes were such a large staple of the diet and so much of a proportion of the people's income was spent on the potatoes, that when the price of potatoes went up, they simply stopped buying other goods and so spent the remaining amount of money on more potatoes. The evidence for this is really not supported Giffen's hypothesis, but still we name Giffen goods after Giffen. Now, let me show you this article, Giffen Behavior and Subsistence Consumption. This is from the American Economic Review in 2008. So American Economic Review is really the world's leading journal in economics. So this is the very best economics journal. And here I've highlighted that this paper provides the first real-world evidence of Giffen behavior. Okay, so more than 100 years after Giffen suggested the idea, the first real-world evidence has been seen. So these things are very rare. In the overwhelming majority of cases, we will observe the law of demand being satisfied. Let's go on paper now and discuss a simple example of a demand function. Our example is taken from the book about the demand for coffee. Okay, so let's have a look at the example for a demand function for coffee. So far we assumed that demand Q is equal to some function d, which depends on three things: the price of coffee, the price of sugar, PS, which naturally would be a complement for coffee, and also income, so consumer income. Okay, so we've got a function of three variables here. Now, we're going to work with a linear function. So this could be, even though we've assumed quite simply that there are only three relevant variables, so that's already a massive simplification of the real world. We're going to make a further assumption that this function d is linear. Okay, so let me just write out. So this has been, we've assumed it's linear, and then once you assume this is a particular parametric form, so if you assume it's linear or log linear or any particular parametric form, you can then use econometrics to analyze the data to provide the best estimates for the particular values. And we've been provided with these. So we've been provided with a constant term 8.56 minus the price P. Okay, so the slope term for this price is just being multiplied by 1, and minus 0.3 times the price of sugar. Okay, so the price of sugar is being, there's this slope term here of minus 0.3, and then plus 0.1 times income y. Okay, so this is a linear estimation for our demand function. Okay, now don't be put off because it looks simple. Linear approximations are incredibly useful. For example, you've studied calculus before, and you know that the derivative of a smooth function is essentially what you're saying by a derivative, or for a function to be differentiable, is to say that locally it can be very well approximated by a linear function. So differentiable functions can be approximated by linear functions as long as we're only looking in a small range. So if we're looking at prices from 0 to 1 million, then the linear specification may be a bit questionable. But if we're just looking in a small region, so for prices between, say, 1 and 10, then this may well be a very good approximation of something that is non-linear on a larger scale. Okay, so that's one point. Also, in general, assuming a linear approximation is incredibly useful. To give an example, we all know, unless we're in extreme denial, that we live on a planet that is spherical, essentially. Okay, so the Earth is round, but we proceed through our everyday life as if the ground is perfectly flat. Okay, so we take a linear approximation of the Earth, which is actually non-linear, and it works very well. We do wonderful things, build buildings and bridges and so on, and very rarely take account for the curvature. So linear approximations are very useful. Now, I mentioned a partial derivative earlier before. Now, you may not have seen this before, so you have probably seen something like this. So if I have a function y, which is a function of x, okay, so we've got y is a function of a single variable x, then you should know quite a lot about how to about calculus in this particular situation. So the derivative, on this course, we'll write it as dy dx, okay? Now, this might not be familiar notation. We can also write df dx as the derivative of this function. Or you may have seen something like this, f prime x, okay? So these are all meaning the same thing, the derivative of y with respect to x, okay? And this is the version that we will use the most on this course, okay? Now, when we have q as a function of 1, 2, 3 different variables, what do we mean by a derivative? Okay, so a partial derivative, which we denote like this. So let's write the partial derivative of demand Q with respect to price, okay? What I'm doing when I take a partial derivative is saying, well, anything that's a variable that's not P, so PS and Y, I'm going to treat as constant, okay? When I take a partial derivative, I assume all the other variables are not variables. I assume they're constants, okay? So here the partial derivative, this is a constant, so it has derivative 0. I get a -1 here, and then this is a constant and this is a constant. So this partial derivative of demand with respect to price here is -1, okay? Essentially, I'm differentiating demand with respect to price and treating everything apart from that price as a constant. Of course, you could do the same. You could take a partial derivative of the demand function with respect to the price of sugar, in this case, PS, okay? And that would be, I'm now assuming that P is constant and I'm assuming that Y is constant, and I would simply get -0.3 as the derivative of demand with respect, the partial derivative of demand with respect to the price of sugar, okay? The partial derivative of the demand function with respect to income would be, well, I assume now, if I'm taking a partial derivative with respect to income, I'm assuming that P is a constant. I'm assuming PS is constant. I'm fixing everything apart from Y. And so that derivative would just be 0.1. Okay? So we'll see these a lot more. And in your mathematics studies, in advanced mathematics in particular, you'll work a lot with these and learn more about what they mean. But for now, just treat it like a basic derivative where we just assume that everything apart from the thing we're differentiating with respect to is being held constant. Okay, so that's what we mean by a partial derivatives, partial differentiation. Now notice in this case here that the partial derivative of demand with respect to price is a negative number. So this demand function obeys the law of demand. Okay, so that's an interesting thing to point out at this stage. Okay, now if we're going to draw a diagram of this, really we've got P, PS, and Y, so 3 inputs, and then this demand quantity Q. So we've got 4 dimensions to this. Now I can't draw 4-dimensional diagrams. I'm sure somebody could, but certainly if we had many more variables, drawing n-dimensional diagrams would simply not be possible. So what we'll do is take specific values for everything apart from the thing we're interested in. So we're going to be interested in analyzing demand as the price of coffee changes. So we're going to take everything else as fixed. So we'll just say let PS equal, for example, 0.2, so 20 cents, and let Y equal 35. I think that's expressed in thousands, so 35,000. And we're going to take them as fixed, okay? In which case we would have Q is equal to 8.56 minus P minus 0.3 times by 0.2 plus 0.1 times by 35, okay? And if we run the numbers, turns out to be quite nice. We get 12 minus P. Okay, so Q equals 12 minus P is the demand function. It's expressing the demand as a function of price, assuming that everything else is fixed at particular values. And now this is an incredibly simple object to produce a diagram for. So we'll do that next. Let's have a look at representing the demand for coffee graphically. Now, the demand function we're given, the demand for coffee, capital Q, is equal to this linear function with 3 variables. So it's equal to 8.56 minus the price of coffee minus 0.3 times the price of sugar plus 0.1 times the consumer's income. To draw a diagram of this demand function, we're going to take the price of sugar as a fixed value at 20 cents. We're going to take income fixed at 35,000. And as we've shown, we can then think of demand Q being just a function of own price alone. Q equals 12 minus P. And then we can produce a diagram of this. So this is what I've drawn on the diagram, a very simple downward sloping linear function. Of course, I haven't really drawn the demand function here, Q equals 12 minus P. What I've drawn is the inverse of this. Okay, so because price is on the vertical axis and quantity is on the horizontal axis, and we're used to expressing functions in this way, y equals mx plus c, should be familiar from GCSE maths or any maths you've seen previously. So because we think of price determining demand, we always express demand functions, demand as a function of price. But this style of diagram was invented long before we thought about demand in this way. So historically, I believe it was Marshall who first drew these types of diagrams. And he thought of demand as determining the price. And so he drew the diagrams what we would consider the wrong way round. Unfortunately, this historical accident is stuck with us now. So when we draw demand functions, we have to invert the function. So I've drawn the function P equals 12 minus Q, simply by rearranging to get P by itself, which was a very simple task here. When we read the graph, we must remember to read it backwards. Okay, so we're going to read off the vertical axis. So I've drawn arrows here to denote the direction of reading this graph. If the price is 9, I read across and down, then demand is 3. Similarly, if the price is 6, read across and down, then quantity demanded is 6. So we simply have to get used to reading demand functions in this way and remember to draw the inverse demand function. When we talk about changes in price in this way, the price changes from 9 to 6, then demand changes from 3 to 6. We call this a movement along the demand curve. Okay, so we don't say demand has shifted from 3 to 6. That will mean something else. We say there is a price change, and so this causes a movement along the demand curve, and demand increases from 3 to 6. So let's have a look at the idea of shifting demand curves. So essentially, when we drew the diagram, we made the assumption that the price of sugar and the price and income were both fixed. So price of sugar was fixed at 20 cents and the price and income was fixed at 35,000. And so these variables collapsed into our constant term 12. Well, let's suppose something changes that we previously assumed to be constant. So if income changes to, for example, 50,000, it's increased from 35,000 up to 50,000. Well then, if we were to run the calculation again, our constant term would change from 12 to 13.5, okay? So if we were to draw this, if I invert this, P equals 13.5 minus Q, I notice that the slope of the demand function hasn't changed. It's still -1. The constant term has changed. So where this function intercepts the axis has changed. And we call this a shift in the demand curve. So when income has changed from 35,000 to 50,000, the demand curve that we're drawing has shifted from the green demand curve labeled D to the orange demand curve labeled D prime. So now if we take income as fixed at 50,000, our demand curve is telling us how the demand for the good will change, the demand for coffee will change as the price of coffee changes, taking the price of sugar fixed at 20 cents and income fixed at the now higher level. So if, for example, the price of coffee was 6, I can read across and downwards to see that the demand for coffee would be 7.5. So now that we've had a look at consumer demand for a good, let's have a look at supply. So when we say supply, we're talking about how much of a good, the quantity of the good that is supplied to a market by a firm. So supply is a decision that is made by the firm that is producing the good. The firm decides how much of a good to produce in order to make profits. Okay, and profits is the difference between revenue, the amount of money that a firm makes, and costs, how much it costs to produce a certain amount of a certain good. So these revenue and costs, anything that affects these is going to affect the firm's supply decision. So for example, the market price of a good is definitely going to affect the firm's revenue. How much can it sell each unit of that good? The firm's production technology and the prices of factors of production, the things it's using to produce a good, so labour, raw material, machines, premises, and so on. All of these are going to go into the firm's costs, and so are going to affect the firm's decision regarding supply. Also, things like government rules and regulations, tariffs, quotas, and so on are all going to be important ingredients for the firm's supply decision. To model the firm's supply mathematically, we use the concept of a supply function. A supply function describes the mathematical relationship between the quantity supplied, typically the goods market price, and possibly prices of the inputs used in production, prices of alternative goods, and so on. A very simple example, if we continue our example based on coffee, so we've looked at the demand for coffee, a simple supply function for coffee could be a supply function that depends on the price of coffee and also on the price of an alternative that the firm could produce instead. So in this example, we're going to say cocoa. So Q, the quantity supplied to the market, is some function S, which depends on P, the price of coffee, and PC, which is the price of cocoa. Although we've only assumed 2 variables are relevant for the firm's supply here, this is still a very general specification. The function S could take any form in general. Typically, we'll think of it being an increasing function of the market price. As we did with demand functions, we're going to work with a linear supply function, and this could be estimated using econometric techniques. And this has been done for us here, so we've got a particular form of supply here where Q, the quantity supplied, is equal to 9.6, so this is a constant term, plus 0.5 times the price of coffee, minus 0.2 times the price of cocoa. So here we have, well, there's 3 dimensions here. There is the quantity supplied, the price of coffee, and the price of cocoa. So if we're going to produce diagrams of a supply function, we need to assume that the price of cocoa is fixed at a particular level. So we're going to take it fixed at $3 and assume this does not change. Then you could calculate that the supply function is Q is equal to 9 plus 0.5 times the price of coffee. So here is a diagram of the supply of coffee. If the price of cocoa is fixed at $3, supply Q is equal to 9 plus 0.5 times P. Now we must remember we're drawing a diagram with quantity on the horizontal axis, so the x-axis, and price on the vertical, the y-axis. So when we produce a diagram of this supply function, we must remember to invert the function. So the diagram actually shows price P equal to 2Q minus 18. And I've obtained this expression by taking the supply function Q equals 9 plus 0.5p and rearranging it to get price on the left-hand side in terms of quantity on the right-hand side. So this pink line, the supply function in this case, or supply curve, is increasing, and it has slope 2 in this particular diagram. It does not have slope 1/2. Now let's adjust the axes because we're going to work with these demand and supply functions a little bit more. So here I've just corrected the axes. This diagram shows exactly the same thing, but you'll notice 2 notches that I've drawn. So I've just in the quantity axis, so along that x-axis, there's 2 little notches where I've essentially removed a piece of the axis. And I've also rescaled the vertical axis. This isn't immediately apparent, but this diagram shows exactly the same demand and supply function we've been working with. Remember, when we read a supply function, we're going to read across and then down. Okay, so if the price is 2, then we read across, and then the quantity supplied to the market is 10. If the price is 4, then the quantity supplied to the market is equal to 11. Now you'll notice here that the linear specification has this constant term, which seems to suggest that if the price is 0, then the firm will supply 9 to the market. Of course, we shouldn't take this too literally. If the price was 0, then of course the firm won't supply anything to the market. So what we might say about this linear specification is that it's accurate within a certain region. So it might not be accurate for all price levels, but for a relevant range of price levels. So for instance, prices between 1 and 10, something like this, then it may well describe the firm's supply behavior very well. Of course, when we get to the extremes, it may not do so well. As with demand, when the price changes, we say this causes a movement along the supply curve. Okay, so we're going to talk about shifts in supply in a moment, but this is not what we mean when the price changes. We say there is a movement along the supply curve. As the price of the good increases from 2 to 4, there's a movement along the supply curve, and the quantity supplied increases from 10 to 11. So what do we mean by shifting supply curves? Exactly as with shifting demand curves, there were things that we assumed to be constant. So we took the price of cocoa to be fixed. Now, if an external shock, so outside of our model, changes the price of cocoa to $6, okay, then rather than drawing a 3-dimensional diagram, we'll simply take this new value and assume that the price of cocoa is now fixed at this new level of $6, and then recalculate the supply curve that we're drawing in this particular space. So in this case, it would be Q is equal to 9.6 plus 0.5 times the price of coffee, minus 0.2 multiplied by 6 instead of 3. And this gives 8.4 plus 0.5p. Remember to invert this, so if we get price by itself in terms of everything else, then P is equal to 2 times Q minus 16.8. We can see that the slope of the supply curve has not changed. What's changed is the intercept term. So it was minus 18, and now it's minus 16.8. So there is a parallel shift of the supply curve. The supply curve has shifted backwards from the pink line S to the orange line S prime. So when there is an external shock of a variable that we assume to be constant, then this is what causes a shift in the supply curve. So now that we know about demand functions and supply functions, we can begin to make predictions about this market. When economists make predictions, we typically predict that the thing that will happen is an equilibrium. Okay, so we'll describe what we mean by an equilibrium in a moment. But essentially, when the market is not in equilibrium, we imagine that there is going to be something that there's going to be some pressure to change the price of the good in the market. Okay, and once we're in an equilibrium, there is simply no pressure to change. So it's like a stable situation. So let's first look at something that's not an equilibrium. So this is what I would call a condition of excess supply. So what do we mean by this? Well, here is the diagram of our demand function and supply function. And let's suppose that the market price is $3. Okay. Now, something very important here to remember is that when we say the market price is $3, this is not something that the firm or the consumer is choosing in this case. Okay, so we're thinking of what's called a competitive market, which means nobody has power, sufficient market power to influence the market price. Somehow the market price is announced. So you could think of what's called an imaginary character, sometimes called the Valrasian auctioneer, whoever this is, or the invisible hand of the market. Essentially, some mechanism announces the market price. And once it's announced, everybody takes the market price as fixed. Okay, so everybody sees this market price and simply responds to it. The consumer sees the market price is $3. And so if we plug that $3 into the demand function, well, we get that the demand is 9 when the price is $3. The firm sees the price is $3. And if we plug this into the firm's supply function, then supply is 10.5 when the price is $3. So there is a difference between the amount being supplied and the amount being demanded. In this case, there is 1.5 million tons of coffee that is not being demanded, but is being supplied. So we call this a situation of excess supply in the market. I've labeled it here with the red arrow indicating the difference between demand and supply in this market. Of course, excess supply, supplying too much to the market, more than is being demanded, is one situation. There's an analogous situation called excess demand, in which case the more is being demanded than is actually being supplied. So let's have a look at this, how this could happen. Suppose that the market price is quite low, so it's $1. Everybody sees this market price and responds. So the demand from consumers when the price is $1 is equal to 11. The supply for the firm when the price is $1 is 9.5. Here, demand is greater than supply. So we call this an excess demand. And I've labeled this with an orange arrow here, which is 1.5 million tons was the units. Okay, so in both cases, excess demand and excess supply, the firms and the consumers were simply observing the price, responding in the way as described by their demand and supply functions, and either more was being supplied than demanded, or more was being demanded than supplied. So what do we mean by an equilibrium price? Okay, now when I describe an equilibrium, I always prefer to describe it as a price rather than an equilibrium quantity, although such a thing exists. So what's an equilibrium price? Well, in this case, let's suppose that the market price is $2. Okay, now if the consumer observes the market price is $2, their demand is equal to 10. And if the firms observe the market price is $2, then they will supply 10. And so there is zero excess supply and zero excess demand. So this magic price level is done all of the work for us. Essentially, there is no excess supply and no excess demand. And so we call this an equilibrium. Okay? Again, notice the important thing here. Price is doing all of the heavy lifting here. Firms and consumers are simply responding to the price, and it may happen that we have a situation of excess supply. It may happen that we have a situation of excess demand. But if the price is just right, if it's this magic price level called an equilibrium price, then supply is equal to demand. So why do we use equilibrium as our prediction for what will happen in this economy? Okay, now this is not a simple question, but one way of thinking about this is to say, well, if we're not in an equilibrium, so if the price is different to the equilibrium price, then there's either going to be excess supply, so mountains of a good that are not being sold when they're supplied to the market, or there's going to be excess demand, so many demands for the good not being met. And in either of these situations, although we don't model this explicitly, you may well imagine that there is a great deal of pressure for something to change. There's going to be incentives for people to change their behavior, pressure on governments, pressure on firms and consumers, and so on. So these are highly unstable situations. Okay. Now, the only time we don't have this unstable situation is when the price is an equilibrium price. If the price is just right, then there is essentially no pressure for things to change. Consumers are demanding a certain level, in this case 10, and firms are supplying exactly the same level. And the price has done all the work, in a sense, to make everyone happy. The way we analyze it is simply to look at any particular price level and ask the question, is it an equilibrium or not? When the price was 3, it wasn't an equilibrium. There was excess supply. When the price was 1, again, we weren't in a situation of equilibrium and there was excess demand. If the price is 2, then magically supply was equal to demand and we are in a situation of equilibrium. Okay, so that's essentially the idea of an equilibrium and how we think about it as we analyze this. Now that we've introduced the idea of an equilibrium in our market, we're going to do an exercise called comparative statics. Okay, now we're dealing with a static model here. We essentially look at a picture of the economy and say, well, if the price is this, then is it an equilibrium? If the price is different, is it an equilibrium or not? Okay, so we're looking at static images of this economy and not thinking about a time dimension as such. And we were assuming that many things were held constant. Okay, so what happens if something that we assume to be constant changes? So let's recall where we are at the moment. We had a demand function Q equal to 12 minus P. And to get this demand function, we assumed that the price of sugar was fixed at 20 cents, and we assumed that income, the consumer's income, was fixed at 35,000. The supply function, Q equals 9 plus 0.5 times the price of coffee. We derived that supply function by assuming that the price of cocoa was fixed at $3. Okay, so we've assumed an awful lot of things are fixed, and then we're analyzing what happens as the price of coffee changes. And if the price of coffee just happened to be $2, so the invisible hand of the market has set the market price equal to $2, then we're in our magic situation where supply equals demand. So $2 is the equilibrium price given everything that we've assumed. Now, we could imagine analyzing what happens as any of these particular quantities change. So let's consider a shock to the price of cocoa. let's imagine that the price of cocoa is increased to $6. Okay. Now, if this happens, then we've analyzed this before, that it causes a shift in the supply curve in our diagram. So supply shifts from the pink line S to the orange line S prime, which has equation Q equals 8.4 plus 0.5 times the price. Of course, we've drawn the inverse of this. P is equal to 2 times Q minus 16.8. So what happens then? Well, if the price in the market for coffee is $2, then we are no longer in a situation of equilibrium. We are now in a situation of excess demand, okay, which I've identified here as the difference between you can see the amount being demanded when the price is 2 is still equal to 10, but the amount being supplied has decreased. So what is the new equilibrium price? Okay, well, in this case, you can solve the equations simultaneously. Supply is equal to demand, taking the new supply function. And if you do this exercise, if the price is 2.4, then you will find that supply is equal to 9.6 and demand is also equal to 9.6. So that would be the new equilibrium price. Okay, so as there is a shock to the price of cocoa, that means our coffee market is no longer in equilibrium. There is some mechanism that is going to make the price want to change, that's going to make everybody want that price to change. And so we won't be in an equilibrium until the price of coffee changes to $2.40. Okay, so this is quite a powerful exercise. We're able to make a solid prediction about the price of coffee in the market once we know the values of all of the other relevant variables. And we're also able now to analyze what happens if there is a shock to something that affects, for instance, the supply function, but we could have chosen the demand function, and see how that changes the equilibrium price for coffee in this example. So now we've developed the tools to analyze supply and demand and the equilibrium price in a market. And we've also performed this exercise of comparative statics. So if there's an external shock that makes the supply curve or the demand curve shift in a particular direction, what happens to the equilibrium price? This is a really simple exercise, but it's incredibly important to develop a good intuition for supply and demand. Indeed, if you have a good intuition for supply, demand, equilibrium, and how external shocks will affect these, then you can have very sensible discussions about economics in all sorts of areas and make very good, quick predictions. For example, if in September 2019 in Saudi Arabia, the oil fields were set on fire, okay? Now you should understand this now as a very large shock to the supply of oil. And hopefully you can guess what happened next. What happened? There was a huge sudden increase in the price of oil, okay? Similarly, another story that you'll see in the news often is, for instance, the Bank of England wants to lower interest rates. Okay, now an interest rate is the price of money, and prices are determined by the forces of supply and demand. So what does it mean to say the Bank of England is going to lower interest rates? Well, it means they're going to shock the supply in some way. Okay, so they might, for instance, flood the market with a lot more money, perhaps by buying lots of government debt. So by developing a good intuition for supply and demand, you suddenly get a much better idea for the workings of many markets and can make good predictions about the directions things will take as external shocks occur. In the next lecture, we'll be looking at a concept called elasticity of demand, which is about the responsiveness of demand to changes in price and other variables. And we'll be looking at an example of taxation and how taxation can be charged to a firm but simply passed on to a consumer. So very interesting stuff, and I look forward to it. In the meantime, take care.